us for this last video in this chapter, where we discussed the regioselectivity of radical halogenation reactions. These radical halogenation reactions that we talked about, that goes through initiation, mainly through propagation. Just don't worry really about showing termination step in a reaction mechanism per se, right? There's going to be some regioselectivity, meaning if you do this reaction not on a methane where the regiochemistry doesn't matter. Regiochemistry just means like where on the molecule the reaction happens. On methane, right, they just could only happen on the single carbon, but propane, there's some choices. The two products that are possible for monochlorination, first is either that molecule or that molecule, right? This is a primary chloride, whereas over here we have a secondary chloride. The difference is that the carbon that's bearing the chlorine is primary here, meaning it's only attached to one carbon. The carbon that's attached to chlorine here in the secondary chloride is secondary because it's attached to two other carbons. Okay. Now the regioselectivity is the following. This is about 40% of the molecules or products is going to be a primary chloride, whereas 60% is secondary chloride. Under a condition like this, remember that means light energy, room temperature. Our task today is to think about why this is the case, why that specific selectivity. Regioselectivity, that word has to do with like how selective the regiochemical outcome is. It's 60% selective for the secondary. Right. To think about how this is going to happen, you also need to think about sort of the statistical factors. And we're not going to do any complicated statistical calculations or anything like that. We're just going to think about the fact that to obtain the primary chloride, right, CH propagation, like this step with the chlorine radical, would have to happen at one of these 6 hydrogens, or one of those 6 CH bonds need to be broken in the propagation step, right? So that's the sort of statistical factors. Right. Now, so if we divide the 40% yield by the 6 hydrogens, right? The reason why we do that is by having six opportunities to make primary chloride. This primary chloride product production is skewed by 6 times hydrogens than, like, say, one hydrogen situation. And if we divide 40% by 6 hydrogens, what we should be able to get is sort of the reactivity ratio of the primary hydrogen as opposed to the secondary hydrogen reaction. And hopefully by the time we're done here, it'll probably make sense. Another way to think about this number is there was a 6.7% yield per each of these bonds. That would add up to 40%, because any of these 6 could have reacted, right? Now let's think about the secondary chloride product. To obtain that, we need to react. We need to see the reaction between one of these 2 CH bonds in the middle. Sorry, that was my wife calling. We'll call her back, but one of these has to be maybe do this. Right. One of these has to be replaced by chlorine, and so the yield was 60% yield, 2 hydrogens, so that's 30% per, well, I forgot to say earlier, per hydrogen. Okay. Now, that again, we were saying that that's kind of a measure of reactivity of secondary hydrogen towards chlorine radical chlorination. So the relative selectivity between primary versus secondary for chlorination is that 30% divided by 6.7% is 4.5. What does that mean? Well, that means we're saying that two secondary hydrogen are 4.5 times more reactive than primary hydrogens in chlorination. Radical chlorination, that is, that's initiated by light. Okay, so that's our conclusion. Okay. Hope that makes sense. This regioselectivity, right? We should be able to explain that with the bond dissociation energy. Because remember, this reaction is just driven by enthalpy. Earlier, we calculated this for the methane situation right here, and we're gonna do that for this primary situation. So to calculate those thermodynamic properties, right, so we look up the primary CH bond, its bond dissociation energy according to the table would be about 101 kilocal per mole. Okay, and then HCl, that's the bond we're breaking. The bond that we are forming is worth 103 kilocal per mole. What does that mean? So the delta H, right, is going to be 2 kilocal per mole. It's a little bit exothermic. It's favorable. It's a favorable step by that much, right? The mechanism will go like that to form HCl. Now, what if it's the secondary hydrogen, right? Then, of course, the mechanism itself would go like so. To do the math here, this secondary bond is worth 99 kilocal per mole bond dissociation energy, and then of course this is still the same, 103 kilocal per mole. So the delta H is even more exothermic. It's 4 kilocal per mole, right? It's 99 minus 103. This is a little even more exothermic. Okay, and also this help us conclude that secondary radical is about 2 kilocal per mole more stable than primary radical. How do we know? Because the secondary radical formation is that much more exothermic by 2 kilocal per mole. Now let's apply this to bromination. Similar results will be obtained, but with even higher regioselectivity is what we observe. The primary bromide is obtained in about 3% yield, whereas the secondary bromide is obtained in about 97% yield among all the products, right? Remember, to obtain the primary bromide, we need those the reaction to happen at one of these 6 hydrogens again, right? So that's gonna to calculate the relative reactivity, we could do 3% divided by 6 hydrogens, and it's about 0.5% per hydrogen. To do the secondary reaction, right, there's only 2 hydrogens, so it's not statistically likely that it happens there, but the reactivity is much higher, right? It's 48.5% per hydrogen. What does that mean? Regioselectivity of bromination then, like before, it was chlorination regioselectivity, and this time for bromination, this is primary versus secondary. To do comparison to tertiary or something, you need to look at the data from the table in the textbook. What does that mean? That means that secondary hydrogens are 97 times more reactive than primary hydrogen in radical bromination. Okay. To do some thermodynamic math here, right? Remember that in this step of propagation, you're breaking the primary CH bond and forming an HBr bond. So this bond here is still worth 101 kilocal per mole, like before. The only new thing is the HBr bond dissociation energy is new. This is only worth about 87 kilocal per mole. What does that mean? The delta H is going to be that difference, which is plus 14 kilocal per mole. Now this time it's fairly endothermic. It's basically an uphill battle here, right? In other words, this is more stable really than that radical. It's not surprising because bromine atom is much bigger. Okay, and then for the secondary, what's the situation here? The reaction is going to be like so. And the data says this is worth, secondary bond, remember, is worth 99 kilocal per mole. I think we used the same number earlier. Yep. And then HBr again is 87 kilocal per mole. Okay. So what's my point? The delta H here is plus 12 kilocal per mole. It's a little less endothermic. And still we come to the same conclusion. It's the secondary radical is 2 kilocal per mole more stable. Than primary. Now, this is what I want you to think about, right? The difference between secondary and primary radicals is 2 kilocal per mole, whether that's in the context of bromination or chlorination, and yet the regioselectivity is vastly different. It's like 97 times difference for bromine. It was only 4.5 times difference for chlorination. So why is that, right? That's what we want to kind of try to understand here. Okay, and to understand that, it has to do with kinetics of the reaction, not just thermodynamics. And to understand that, we need to look at the reaction energy coordinate or reaction progress energy diagram. So let's think about that for chlorination first, right? So chlorination reaction, remember, it was overall exothermic, right, if you recall. So I'm gonna have this at the top, and then primary radical is a little more higher energy than secondary radical plus HCl formed. And we're going to say that this energy difference is 2 kilocal per mole, right? And it's the same situation for bromination, right? It was endothermic, so I'm going to put this down here, relatively speaking. And it was endothermic, you had to gain energy. But still, this energy difference is still the same, 2 kilocal per mole energy difference. Okay, now, so the end result is really the same, right? Between these two, it's only 2 kilocal difference, it's only 2 kilocal per energy difference. So like, why is it that you see so much more differentiation between primary and secondary for bromination than for chlorination? So let's think about the energy diagram, what it would look like for the secondary path, right? It goes through some sort of a activation energy, so it's a little bit of a energy hike, and then you get that this is the transition state between this step and that intermediate. And then to get to the primary, you might have to overcome a little bit more activation energy, and it ends up there. Okay, now for the bromination, transition state is higher than the intermediate that you settle on, so it must be like that. Now for the other species, it must be like that, right? The transition state. Now, what does that tell us? Well, that tells us that there's only about this much difference in activation energy. The delta or difference in activation energy here, but the activation energy for the two pathways for bromination would be that much more. Okay. And indeed, this is around 1 kilocal per mole difference, whereas here it's about 2 kilocal per mole difference in activation energy. These are not numbers we have calculated yet, but hope that makes sense, right? Like, this is the activation energy for the secondary. This is the activation energy for the secondary once again. Right. What does that tell us? Well, that tells us that because the chlorination is exothermic and the transition state looks more like the study material, there's not much difference in activation energy, and so there was not much of a selectivity between these two things. even though thermodynamically the difference is the same as that of bromination situation. But here, because it's endothermic, you have to climb up. There's quite a bit of difference at the transition state top, right? And so for that reason, there's going to be quite a bit of difference. It's kind of like if you imagine, right, like if somebody wants to take this orange path versus green path, if it's a mountain like that where you don't have to climb much, there's really not much difference between the two paths. When you have to climb this much to get there, there's quite a bit of difference in energy you have to put in to climb that mountain. So there's going to be a lot more people taking this easier route than the other one, right? That's the selectivity. Hope that makes sense. So it has to do with the difference between the reaction being exothermic versus endothermic. Another way to think about this is transition state here that differentiates the two look very much like the products, and so there's selectivity just like the products for bromination. Okay, we would say that the chlorination reaction or exothermic reaction, the transition state is closer to reactants. In other words, if you look at the transition state, there's not that much bonding happening between H and Cl, right? Whereas the transition state for endothermic reaction looks much closer to, so this looks very much like the study material, whereas for endothermic reaction, the transition state looks very much like the products, right? So if there's difference in products, there's going to be difference in transition state, therefore it's going to be a lot more selective. Okay. There's a much larger delta activation energy, hence there's more selectivity. Oops. Okay. And that's always common in endothermic reaction. Okay. Now, this finding that whether the transition state looks more like the study material, where there's no differentiation, or the transition state looking more like products, where there's differentiation, that has being, the latter situation being more selective, that observation's called Hammond's postulate, which says related species that are closer in energy are also closer in structure, and the structure of a transition state resembles the structure of the closest stable species, whether it's the reactant or product. To sort of rephrase that in an easier term, to break it down to be a more simple explanation of Hammond's postulate, this transition state is kind of early. That's sort of the jargon. That means where there's no differentiation, right? This transition state is closer to where there's no differentiation between the two products, so there's no selectivity. Bromination is the opposite of that. There's much differentiation because the transition state, we would say, is kind of late. That's the lingo. Now, another way to simplify this is exothermic reaction tends to not be very selective. More endothermic type of reaction, tends to be a selectivity because of the difficulty of sort of climbing that mountain of activation energy. So to summarize all of that, right, chlorine or chlorination propagation step, where it's exothermic, It's not very regioselective. Whereas bromination reaction, propagation, where it's endothermic, it's a lot more regioselective. Right, we saw that there's much more secondary product than primary. Okay, so that's a general principle that we could apply to reactions where there's a few different possible outcomes. If it's better, if it's a little bit more endothermic, then it tends to be a more selective reaction. Again, that's Hammond's postulate.